Hi everyone, good morning. My name is Kevin Wizeng and today I'm going to talk about my topic performance comparison of copper and palladium metal semiconductor Schottky diode. Or I begin to do this project because there is less reports available regarding copper zinc oxide Schottky junction diode and the low device performance for copper zinc oxide Schottky junction diodes. So, objective for this project are to fabricate copper zinc oxide and palladium zinc oxide metal semiconductor Schottky device and to investigate the device performances of both samples. Okay, let's have a little background about zinc oxide. Zinc oxide exhibits a large and direct bandgap of around 3.37 electron volt and large exciton binding energy of 60 milli-electron volt at room temperature. Furthermore, zinc oxide has the ability of taking many different forms of nanostructures, such as nanobelts, nanoflowers, nanowall, and nanorods. And due to all of the advantages it provides, zinc oxide is selected as the semiconductor in this project. Besides, zinc oxide has shown some promising results in electrical and optical fields such as photodiodes and LEDs. Okay, let's proceed to the sample preparation. Okay, firstly, the ITO glass is cut into a desirable size and undergo ultrasonic bath to remove some unwanted stain. The ultrasonic bath is carried out by dipping the ITO glass into deionized water for 15 minutes and then followed by ethanol for 15 minutes and then followed by acetone for 15 minutes and then finally by deionized water again for 15 minutes. After the cleaning process, the sample is sent to a deposition process. Zinc oxide seed layer of around 200 nanometer is deposited on top of the clean ITO glass by radio frequency sputtering. And then the sample is sent to annealing at 350 degrees Celsius for 30 minutes. After that, after that, after that, zinc oxide nanorods are grown on the sample by chemical bath deposition. The parameters used for chemical bath deposition is 96 degrees Celsius, 3 hours duration, and 0.05 molarities of precursor solution concentration. Annealing process is carried out after chemical bath deposition at 350 degrees Celsius for 30 minutes. And then metal contact of around 100 nanometer is deposited on top of zinc oxide nanorods by DC sputtering. And finally, the sample is again annealed at 350 degrees Celsius for 30 minutes. The fabricated device is then characterized by FSAM, EDX, XRD, UVB spectroscopy, and an IV test. Okay, so here is the FSAM, and from the figure we can see that the zinc oxide nanorods exhibit a word-side hexagonal shape and it has grown at a high density, covering most of the image. Based on the image, we can clearly see that the zinc oxide nanorods grow along C-axis with a slightly tilted angle. The average length for the zinc oxide nanorods is 1.182 micrometer and average diameter is around 47.44 nanometers. And this brings us to an average aspect ratio of 25. The table on the left shows the diameter distribution of nanorods across the whole area, while the figure on the right is histogram. The number of nanorods in each diameter category and its percentage has been tabulated on the table below. The nanorod grown has a density of 8.97 times 10 to the power of negative 5 number of nanorods per nanometer square. And here is the XRD analysis. We can see that the high intensity peak is centered around 34.4178 degree, and this is the only peak that contributed by zinc oxide nanorods. The other peaks are generated from the ITO glasses based on the database. And the peak at 34.4178 degree has a low full width half maximum value, which indicates the zinc oxide grown has a high crystal quality. And from the database, the peak list is from 002 along C-axis. This result is aligned with the FISM image that we saw earlier. And the table here is the parameters extracted from the XRD analysis. The sample is having a 2 theta of 34.4178 degree and full width half maximum of 0.156, crystalline size of 55.66 nanometer, d-spacing of 0.26036 nanometers, lattice constant C of 0.52072, and strain of 0.012%. Let's do the UV visible analysis. The graph on the left shows the top plot of the sample. Based on the graph, the energy band gap for the sample is 3.255 electron volt. This value is slightly lower than the theoretical value of 3.37 electron volt. This difference may due to the lattice strange and structural defects in the zinc oxide nanorods. So here is the IV characteristic of the two samples, which are copper and palladium Schottky diodes. Based on the graph on the left, we can see that the current gain for copper sample is lower than the palladium sample. If we set the reference point at 2 volt, the current to voltage ratio of copper and palladium is 5.763 times 10 to the negative 7 and 5.06 times 10 to the power negative 5 respectively. Based on the graph and through some calculation, we can extract the other parameters such as rectifying ratio, threshold voltage, Schottky barrier height, and ideality factor. The copper rectifying ratio is 1.07, while the palladium rectifying ratio is 87.84. The copper threshold voltage is 5.6 volt, while palladium threshold voltage is at 1.62 volt. The copper Schottky barrier height is 0.66 electron volt, while the palladium Schottky barrier height is 0.43 electron volt. And finally, the copper ideality factor is 6.1, while the palladium ideality factor is 5. From all of the data, we can clearly see that the palladium sample outperformed copper sample in every aspect. And finally, here is the graph of the metal semiconductor metal configuration of copper and palladium sample. Based on the graph, the palladium sample is again outperform copper sample. So, in conclusion, selection of metal contact is important in determining the performance of Schottky diode. A higher work function metal such as palladium will ensure that the metal semiconductor interface is highly Schottky behavior, which will enable high rectifying characteristic, improve the threshold voltage and the current flow. So, palladium is a better candidate than copper in the application of electrically pumped random laser due to the high current flow. For our future work, we would like to fabricate an electrically pumped random laser device. Based on our knowledge, metal semiconductor junction alone is not able to create an electrically pumped random laser device. So we think that this can be achieved by introduce an electron blocking layer at the metal semiconductor interface so that the recombination can occur. And the figure here is the design of our device. And thank you.